Hello, Chem 1. Today we're going to talk about a pivotal key concept within chemistry called the mole. It's huge in Chem 2. We're going to use it for the next 3 weeks plus. It's a counting concept, it's a measuring concept, it's a pivotal concept to chemistry. Before we get started, a couple things administrative wise. First, apologize for yesterday's video. Obviously, there was a snafu and my microphone was not working and I posted it, and I'm sure you guys liked listening to my video just the way you'd like to listen to me with me on silent or mute. So apologize for that. So let's get to it. So as a warm-up, using the concept of this mole that we're going to deal with, I'm going to pose a question that has nothing to do with chemistry. If I know that if I take a roll of pennies got like 50 pennies in a roll, take a roll of pennies, I put it on a balance, it weighs about 126 grams. I actually did this to make sure that the number was reasonable. If I had a big pile of pennies, and this amount, 41.7 kilograms, is a big pile of pennies. If I had a big pile of pennies and I wanted to figure out approximately how many rolls could I make, how would I figure that out? So go ahead and think about that for a second. You can go ahead and pause the video, give yourself a little bit of time, and maybe even come up with a number. Let's see how you did. So let me show you how I would do this. I would first and foremost, the first thing I would do is change those kilograms to grams. Why? Because my roll of pennies is in the measurement of grams, so I want to make sure I can compare the two. So if I take 41.7 kilograms, there's 1,000 grams in a kilogram. Do my math, I find that is 41,700 grams of pennies in my pile of pennies. And then this is the part that you might have done a little bit differently. You might have just automatically just punched it into the calculator thinking about what should be done. But I would think about it this way. I'd say I'd take my 41,700 grams, and since there are 126 grams in a roll, see, what I've developed here is a conversion factor where the bottom and the top are the same. So the 126 grams is the same as a roll. So allowing me to cancel out the grams, and I find out that I could make about 331 rolls of pennies. That's assuming they're all the same weight. We know from our Pennium lab earlier in the year that that's absolutely not the case, but it's good to hope that that could happen. Should give a really, really good estimate. So what's this got to do with chemistry? Well, we're going to use a unit of measurement called the mole. Now, in October of every year, October 23rd to be precise, is Mole Day. October 23rd is Mole Day. Mole Day is celebrated to talk about this concept of the mole. And actually, chemists from all around the world get together. A lot of chemistry classes do something a little bit special for the mole. These images on the screen are from the Mole Day celebration. The one in the right-hand corner happens to be from a greeting card that was generated for them. But moles are a very pivotal part of chemistry. Now, not the furry little moles, but a unit of measurement called the mole. So what's it got to do with measuring? Well, if I were to say, go get me a couple of eggs, you'd probably get me two. If I were to say, I would go to Dunkin' Donuts. Oh, sorry, no, it's no longer Dunkin' Donuts. Dunkin'. I would go to Dunkin' and I would say, I would like to have 2 dozen donuts. They would give me 2 times 12 or 24 donuts. If I were to say, this car I bought, it cost me, 25 grand. Well, I know that grand means 1,000, so that's $25,000. There are words associated with measurements, and we naturally use that measurement as a way to describe a certain number. It's easier, okay? And there's a lot of them on the screen that you've seen before. Did you know a gross was a dozen? That's 144. That's why that number's there. It's a dozen. Okay. And do you know the century? High school was named Century because it was finished being built in the turn of the century. Bet you didn't know that. Didn't open until 2001, but was finishing being built in 2000. Okay, here we go. So what is the mole? Well, the mole is what we use to count things. And think about what the things are that we count. We would probably want to count things like atoms or molecules or any type of uh, compound. We're looking at different things that we might want to count. The chemistry things. The chemistry things are atoms and compounds. We use it. It's often referred to as the chemist's dozen. And it is literally the international standard, the SI unit for the amount of something. When you're counting things in science, you usually use the mole. So how big is a mole? Well, let's think about this really for a second. The thing we're going to be counting, atoms, molecules, are really, really tiny. So if we want to count a number of things and have the number of things be tangible, be something we can see and appreciate the size of, the mole number is going to be really, really big. So if I had a mole of marbles, if I had a mole of marbles, I would, if I would put them on the earth, try to store them, they would cover the earth, the entire earth, to a depth of 50 miles. It's a lot of marbles. If I had a mole of paper, the pieces of paper, and I would put them, stack them on top of one another, like stack them on my desk, and I would stack it. They would go all the way from here to the moon and back 80 billion, billion would it be? Billion times. That's a lot. Just think about it, to visualize or conceptualize how big a mole is. Well, it also, if I had 18 milliliters of water, okay, 18 milliliters. 18 milliliters are about the size, a little bit bigger than a golf ball. Okay, so a golf ball is a little bit, is probably about 15 milliliters. So a golf ball, if I had something a little bit bigger than a golf ball, and it was just pure water, I would have 1 mole of molecules. Think about that. I have as many molecules of water in that small space of a golf ball as there are in all the pieces of paper that it would take to go from here to the moon and back 80 billion times. That's a lot of molecules. So since in chemistry we deal with very, very small things, atoms and molecules, we need a very large number. If I were to go to Dunkin' Donuts and use the unit of the mole, and I want to have a reasonable number well, let's just use the grand. Okay, so we know a grand is 1,000. If I wanted to if I didn't know the concept of the dozen, okay, I'm going to go to the dozen for a second. Didn't know the concept of a dozen, but I did know the concept of, say, the grand. I'd have to say, well, give me 1/100th of a grand. That's just awkward. So using numbers that are tangible, that are reasonable in size, help with documentation, vocabulary, and such. The things that we're counting are really, really small, so that the number we need is really, really big. So since we're counting really, really small numbers and with a really small things with a whole lot of those things, the mole is really, really big. So what is the mole? Well, by definition, the mole is the number of atoms that are in exactly 12 grams of carbon-12. This guy up here, guy's name is Amadeo Avogadro. Amadeo Avogadro determined what that number was. Amadeo Avogadro determined that the number of atoms in exactly 12 grams of carbon-12 is 6.02 times 10 to the 23rd. Let's think about how huge that number is. That is, let's see if I can get my pen to work. That is 602 000 000 000 1 2 3 4 000 000. That is a very, very, very big number. Those are not decimals, those are commas. It's a huge number. So because it is so astronomically huge, it's like a quadrillion, or a quintillion, something like that. 1 million, billion, trillion, quadrillion. So it's it's 602 million quadrillions. That's crazy. Okay. Anyway, so because this number is so huge, and yes, not to belittle ourselves, yes, we in chemistry are that lazy. We do abbreviate the word mole, M-O-L-E, with the abbreviation M-O-L. We just dropped the E. A mole is the number of particles, 6.02 times 10 to the 23rd particles in a mole. So what's a particle? Particle is maybe a gram, maybe a atom, maybe a molecule, maybe a formula unit. The difference between molecule and formula unit is molecules are covalent and formula units are ionic. So you talk about an ionic compound like salts, potassium nitrate, we have the potassium permanganate, lead to sulfate, those are all ionic compounds, and molecules are things that are held together with covalent bonds like phosphorus, trichloride, water, carbon dioxide. But they're still just compounds, the individual compounds of atoms being clumped together. So let's see how we use this. So let's look at our first example. Our first example would say, how many atoms of lead are in 0.54 moles of lead? And we're going to use this concept of dimensional analysis, which we're going to use a whole lot here to lay out our work to make sure that we don't make any mistakes. So we always do the same thing. We always start with whatever's given to you. Whatever's given to you goes down first. And once you write down what's given to you, then you need to figure out what conversion factors to use. Well, since we know 6.02 times 10 to the 23rd particles is a mole, we have two conversion factors. We have 6.02 times 10 to the 23rd atoms on top of a mole, or we have the mole on top of 6.02 times 10 to the 23rd atoms. What do we have? A conversion factor. Each of these equals 1 because the top and the bottom are the same amount. 6.02 times 10 to the 23rd atoms is equal to a mole. So each one of these is 1. So all we're going to do is take our number of moles and we're going to multiply it times 1. But we're going to change the units. We're going to change units. We're going to change from moles to atoms. Example, when we did in the beginning, we wanted to figure out how many grams are in this 41.7 kilograms. We multiplied times the conversion factor where the top and the bottom were the exact same measurements, just expressed in different units. So we could use either one of these. If we choose to use this one, the one on this side, let's see if I can get this to work. Go back to my get rid of my pen. If I were to use this one, notice that nothing cancels. Okay, moles are on top here, but atoms are in the bottom. Nothing cancels. So I know that's the wrong conversion factor to use. I want to use this one. So if I use this conversion factor, again, looking at it, you see that moles are on top, moles are in the bottom, so those units are going to cancel. Okay, those units are going to cancel. And when those units cancel, I'm left with atoms. And when I'm left with atoms, when I'm left with atoms, I have to click my little thing. Go back to my pointer option, get rid of pen. When I click go to atoms, I get 3.3 times 10 to the 23rd atoms. Okay, I do the math. 0.454 times the number gives me this. And this is what you get from the calculator. If you don't have a calculator out already, pause the video, go get a calculator, because you're going to want to make sure that you can get these numbers and use your calculator correctly. This one's not where the problem comes in, it's on the next one. So let's look at the next one. If I have 7.96 times 10 to the 25th molecules of carbon dioxide, how many moles is that? Okay, so again, first things first, you always start with the given, and then I have a choice to make. I have two conversion factors. 6.02 times 10 to the 23rd molecules is a mole, and a mole is 6.02 times 10 to the 23rd molecules. So one of the two I'm going to use. So if I pick this one, again, molecules are not going to cancel. Molecules are on top, moles are on the bottom. That doesn't cancel. I want to use this one. So if I use this conversion factor, molecules are on top, molecules are on the bottom, they cancel. Okay, and when they cancel, I'm left with just the mole. And then when I do the math, I get 132 moles. Now this is one where I definitely need you to use your calculator and confirm that you get this number. It's very, very common to make a mistake with your calculator and not be able to get this number because you when putting this 6.02 times 10 to the 23rd into your calculator, it gets broken up. I'd strongly suggest if you have a Texas Instrument calculator to go ahead and use the functionality of the calculator itself. It has an EE button or an EXP button that allows you to type in 6.02 EE23 to be the equivalent of the 6.02 times 10 to the 23rd. I'd avoid using the caret on your calculator because sometimes that's problematic and you forget to put parentheses around things and it messes things up. If you happen to do the math here and you got like 1.32 times 10 to the 40, I guess it'd be 50th, then you did something wrong. Okay, last example for this video. How many atoms of oxygen are in barium sulfate? Well, barium sulfate is BaSO4. So we're talking about the atoms that are in that compound. So the first thing we want to do is find out how many molecules of barium sulfate we have. How many molecules of barium sulfate we have. And we're going to do that by looking at the two conversion factors. Again, 6.02 times 10 to the 23rd molecules and is equal to a mole, or a mole is equal to 6.02 times 10 to the 23rd molecules. So which one are we going to use? Left or right? If you chose the left, you are correct. The left one is the one we want to use because the mole's on the bottom, so our moles can cancel. Moles are on the bottom, so our moles can cancel. And now we're left with molecules. But we have to ask ourselves, how many atoms of oxygen are in one molecule of barium sulfate? And if you look up down here, you can see that there are 4. So since we know that there are 4 atoms in each molecule, I've developed a second conversion factor. So if I go ahead and use that correctly, again, making sure my molecules cancel, leaving me with only atoms, then I do the math, 0.35 times 6.02 times 10 to the 23rd times 4, I get that there are 8.4 times 10 to the 23rd atoms of oxygen in that barium sulfate. Okay, so that shows how to use this concept. On YouTube, there's going to be another video called Sig Figs Matter that is going to help with understanding how to round these numbers. And I would actually consider not doing the homework associated with this section until you've watched both that video and this one, because you might get some answers wrong because you round things wrong. And the next video will explain a little bit better how to round things. So that video hopefully will be out today. It was out yesterday, but in silent mode. So we'll see what happens. Anyway, take care, be healthy, be safe, practice that social distancing, and I hope to see you real soon back in the classroom.